Okay, welcome back. In this video, we're going to continue talking about electric fields, and we're going to discuss how to calculate the electric field of a charge distribution. But first, we're going to do a quick practice problem. And in this problem, we want to determine where the electric field is zero if we have a 2 millicoulomb charge that is located at the origin and a -3 millicoulomb charge located at 1.0 meters. So here's the origin. Here is our +2 millicoulomb charge. You can call that Q1. And 1 meter away, a little bit touchy. 1 meter away is the -3 microcoulomb charge. Now, just to be clear, this is just -2 here. Sorry, +2 at the origin and -3 at 1 meter. Okay, so we want to find a location where the electric field is going to be zero. And one thing to keep in mind is that we want the magnitude of the electric field to basically cancel. So we want the magnitude of the field from charge 1 to be equal to the magnitude of the field from charge 2. But first we have to think about where this can happen. And so what we do is we split up space into sort of 3 regions. One region is to the left of both charges, the second is in between, and the third is to the right. And then we think about what would happen to a positive test charge if we put it in that region. So first of all, region 1, positive test charge would be repelled from the 2 millicoulomb, and it would be attracted, so that would be E1, and attracted to Q2. So it could possibly be region 1. Region 2, we put a positive charge, it'll be repelled from charge 1 and attracted to charge 2, so region 2 is not going to work. Region 3, we are going to be attracted to, let's draw that a little bit better. We'll be attracted to charge 2 and repelled from charge 1. So you might think that region 3 could also work. But it turns out that since we're closer to the larger charge in region 3 is not going to work. So the only one's going to work is region 1, and we can just label this distance here x. Okay, so we want to search for that position x. And we're just going to do a distance, not a displacement. So we're going to pretend like we're starting at 0 and going to the left. For that reason, if I then wrote the magnitude of E1, it would be k Q1 over R1 squared, and the magnitude of E2 would be k Q2 over R2 squared. And this would be a magnitude. So that means that when I put in Q1 of +2 millicoulombs, I would have 2 millicoulombs, and then R1 is the distance from Q1 to the test charge, little q, and that distance will simply be x, and we square that. Then for Q2, that's going to be -3 millicoulombs, but we're taking the magnitude. We've already used our diagram to establish direction. Okay, but our distance will be x plus 1 squared because we're starting at Q2. So the millicoulombs will cancel, and then we just need to solve 2x plus 1 squared equals 3x squared. Okay, now one thing that you can do at this point is take the square root of each side, or you could carry this through and you would have 2x squared plus, let's do our math correctly, 4x plus 2 equals 3x squared, or that just tells me that we're going to have x squared minus 4x minus 2 equal to 0. Okay, so x is going to be equal to 4 plus or minus the square root of 16 minus 4, 1, -2, and that's all over 2. So let's do a little bit of math. That's going to give us 24 in there. So it's going to be the square root of 24. Probably the easiest way is going to be 4 plus or minus 2 root 6 over 2. Okay, so we simplify that and we get 2 plus or minus root 6 as the position of x. Okay, and then we just think about this, and we don't want to have a negative number for this, so our distance would actually be 2 plus the square root of 6. Okay, so our final answer would be 2 plus root 6. And remember, we don't want to have a negative number because a negative number in our case would be heading into region 2. Okay, so that's how we go ahead and solve for where the electric field is 0. Now, one limitation of Coulomb's law that we have talked about is that it's only good for point charges or spherically symmetric charges. Okay, and that was where you had a point charge Q or a sphere of charge Q. And we'll talk more about why this is a bit later on. But what we need to do for more complicated continuous charge distributions is we need to break that distribution up into little pieces and then use superposition to find the electric field. So this got cut off, but at the bottom it says, at a given location in space near the charge distribution. So that just says distribution. Sorry about that. So how do we do that? Well, we have different types of charge distributions. When we have a wire or a ring or anything that is linear in its geometry, we talk about a linear charge density lambda. Now, lambda could be equal to a number of things. Lambda, because it's a density, could be charge per length, where we have Q for the entire object and L is the entire object. So in other words, a macroscopic measure. Or we can split the object up into little chunks. And this little chunk has a little bit of charge, dq, and it has a little bit of length, dl, which we sometimes will write as dx. So this could also be dq dx. So that's what a linear charge distribution would look like. We could also have a surface charge distribution. And this would be a two-dimensional object, and we signify that with sigma, which is charge per unit area, and that's charge divided by area, or dq over dA. And so if we think about a little surface segment of this, this would have charge dq and area dA, whereas the entire thing would have a charge of q and an area of A. So again, we can set this up either way. And one thing to point out here is that means that the charge, which we'll use this later, is equal to sigma times the area. So keep that in mind. Likewise, dq is sigma dA. Okay, now our last type is the volume charge distribution. And the volume charge distribution, is when we have a three-dimensional object. Okay? And we talk about this is actually, a volume charge density, which is charge per unit volume. I apologize for that error. And so that means that we can take a volume element, dV, which contains charge dq. So that means that rho is defined as q over v, or dq over dv, which means that the charge is equal to rho times v, or dq is rho dv. Okay, so what's the basic outline for doing electric fields? First, we're going to divide an object into small parts. Each part has a small charge dq and a total charge of big Q. But what this small charge dq will do is it will create a tiny electric field dE at a point in P in space, a distance r away from dq. For example, if I have a rod I have a point P right here, which is a distance r away from the rod, and I have a chunk right here, dq, it will create, assuming it's positive, a field dE, which goes like this at point P. Remember, it's a positive charge, so if I put a positive test charge, it'll be going away. So what we can do is we can add these fields dE together to get the total field at point P. And what does that sound like? You guessed it, that is an integral. So the electric field, which is still a vector, is an integral of all the dE's. And this right here is the main thing to remember. Okay? Now what we do with dE is we turn dE into k dq over r squared. And then our job is to turn dq into a spatial variable. So for example, we saw earlier that using lambda equals dq over dx, we can write that dq is equal to lambda dx. And so what we're doing is we're turning a charge variable dq into a spatial variable dx. And it's linked together by that charge density. So we need to find a common variable, in this case, the charge density, that r and dq both depend on. Then it's often useful to use symmetry and trig to simplify the problem by eliminating off-axis components of E. And what we mean by that is that sometimes the geometry will allow pieces of the electric field to cancel, and we'll explain that further. Finally, you put in limits to the integral and you evaluate it, and hopefully you get an answer that makes sense. And this is cut off, but the last point to make is that you really want to spend time setting things up. That's where all the good physics is. Okay, so here's an example. We're going to calculate the electric field magnitude and direction a distance y away from an extremely long straight wire of charge density lambda. So what I'm going to do now is I'm going to set it up, and then we're going to carry out the integral in the next video. So one thing that we want to keep in mind is that lambda in this case is going to be equal to a couple of things. It's either going to be the entire charge divided by the entire length L, which we don't know, but it's just a variable, or it could be dq dx. And that means, of course, that dq is going to turn into lambda dx. Now, really what I should be doing is writing this as a lowercase q, because it's a small amount of charge, so we don't want to be misleading. And after all, when we set up our integral, we're going to be integrating small amounts of charge. Okay? Okay, so the first thing that we do is we pick a chunk of this wire. And so here is a chunk of the wire. Okay? And this wire is going to have charge dq, and it will extend for a length dx. Okay? Now what is this wire going to do at point P here? Well, if you think about it, there's going to be, I can't draw a dotted line today. There's going to be an electric field at point P that goes approximately like this. And that is what we're going to call dE, the differential of the electric field. Now we have to realize that this dE has components, and we would call that dEy and dEx. And what we can do is we can label an angle here theta, which is also this angle theta. And we can realize that the only thing that's going to contribute to the field is dEy. So in other words, the dEx's will cancel. And the reason for this is that on the other side of where we're located, there's going to be another chunk right here, which is going to cause another field going this way, which will have an X, which will cancel out. Okay? So that means that the only thing that's going to be left is DEY. So really what we want to be calculating here is the electric field as the integral of DEY. Okay? Now we can see from our diagram here, I'm just going to erase this dq dx. Maybe not. And it's frozen, so I'm going to pause for a second and sort this out. Okay, so we've sorted that out, and this is actually going to be the integral of dE, and if we look at our diagram, we're going to want cosine of theta. We would then substitute that dE is k dq over r squared, and then we have our cosine theta. Okay, so we're going to stop here, and next time we're going to look at how we take this and integrate it to find the electric field.